Hello, students. We are into 3-5, and I've got a couple pieces that came in. So let me check here. So it says 3-5, question 7. Okay, so let's take a look. Question 7. Suppose all operations result in whole numbers. Explain why this is true. Oh, okay. Well, right now, later in the course, we will see that division really, doesn't exist. We would be multiplying by what's known as the multiplicative inverse. We won't get there until chapter 6, but that's what we'll get to later. But for now, we actually can still figure this out just with the definition of division. So let's take a look at what that would look like to us. Let me get a little white space in here. Let's see here, change my color. Okay, so here we go. There goes that. Pull it down just a little bit. Okay, and we'll toss a little bit more of it over there. Okay, so now let's talk about this. How do I want to say this first? So what we want to do is use the definition of division. Now, just remember, what does it mean? So kind of take the left-hand side, and we'll just say, okay, let's say that a minus b divided by c is equal to some number. And I'm going to choose one of the letters that's not chosen in here, so I just don't mix them up. I'm going to call it d. Okay. So what does that mean? Well, a minus b, this quantity divided by c, is equal to d if and only if what? If and only if a minus b is equal to what? C times d. All right. So now when you look at this, right, you say, well, wait a minute, what is really happening here as I have it, right? And we could look at the other side. Now, this other side, a minus, or a divided by c minus b divided by c. So I may not know what that is equal to. But I could write that as a divided by c. And again, I don't know what this one is equal to. So I want to choose a different symbol, let's say. So let's say this is equal to e, and b divided by c is equal to f. Okay. All right. So now this is true if and only if a is equal to c times e, and down here, if and only if, what do I have here? B is equal to c times f. Now I chose different ones, and what I'm hoping at the end of the day is I'm really hoping that the left-hand side, which we just said is d, so I'm really hoping that d is equal to a divided by c, which is e. I'm really hoping that this is true. This is what I hope is true. This is my hope, but I can't assume that it is true yet. So I have to explain why it's true. Okay, so I'm going to cross that off for now because I can't guarantee it. Okay, so now what I'm going to do is I'm going to take these two quantities. I'm going to say, okay, well, let's do this. Let's do a minus b, because that's what I have up here. And what does this equal here? A minus b is equal to CE minus CF. And each of these has a common factor of c, which means a minus b is actually equal to c times e minus f, right? Well, what is e minus f? Well, it is some quantity. Take a look here. This quantity, this single number, because operations have to result in a whole number, that I multiply by c gets me to a minus b. So by definition, that thing that I multiply by c to get a minus b has to be unique. And so this is the same thing as saying a minus b must be equal to c times d. So what I have now is that d is equal to e minus f. And if d is equal to e minus f, then d, which I defined right here, is equal to a minus b divided by c. And e is a divided by c and F is B divided by C. So all this did to get to this stage was use the definition of division. So I said, I don't know what this is equal to. I'll call it something. I don't know what these are equal to. I called them something. And then I use that definition of division to turn this back into an equation that doesn't actually have division at all. And so now I can show that A minus B is equal to something, dot, dot, dot. And once I get to the end, I can actually say, hey, I know those two have to be exactly the same. So pretty cool use of the distributive property or factoring. And again, at this point in time, we do not have a factoring, or at least it wasn't given to us as like a guaranteed rule that everything does distribute this way. But this is a really nice way of actually showing that, yes, there is a distributive property of division, but it's one-sided. Yeah. So let me see here. Let me go to a new share real quick with just a whiteboard screen. So the reason why it's one-sided is you can have A minus B, and if you take that and divide by some number, you're going to get A divided by the number minus B divided by the number. And I'm just giving you this because I think it's really helpful for you to think about this as you go forward. You could also have, I'm going to put a plus sign in here because it could be plus or minus. Okay, it could be addition or subtraction. Okay, so now what I'm going to do is I'm just going to rewrite this over here. This quantity, if I write it in fraction division form, A divided by C, plus or minus B divided by C. What you'll notice is they have the same denominator, and the same denominator, I would add the top or the bottom or subtract the top or the bottom. So I end up with the exact same thing. So this is kind of like thinking of what you do when you had fractions. So I'm trying to connect the concept that you've already seen before. When you have like denominators, you can do this. And so this is really kind of a like denominator approach. But you can't go the other way. So what does that mean? I can't do A divided by B minus C and say that that is A divided by B minus A divided by C. Oops, I went and did division slightly different. So these, you can check these if you wanted to. And if you look here, if you think back to the fraction idea, that would be like saying A over B minus A over C is the same as A over B minus C, but we would not subtract. You don't subtract denominators when you're dealing with fractions. And you can, of course, try numbers in there if you'd like to. So personally, I think this one's a good one. The second one's a good one to actually pick some numbers with, because I think that is pretty helpful. And usually, like my go-to for something like this is I'd like one side to divide evenly. So for example, I might pick like a 4 minus 3, because 4 minus 3 would be a 1. So that's probably what I would do. And then I prefer, like if I'm working with younger kids, I want to make sure that what I'm showing them, oops, let me get back to my drawing here, divided by B minus C. So I want to make sure that what I'm showing them does divide evenly for all the numbers. It's easier when you're seeing it at first. So if you think I need something, here's the 4, there's the 3. I need something that divides evenly by 3 and by 4. So I would probably choose 12 is probably what I would do. Okay. So let's take a look here. So if I had this, it would be 12 divided by 4 minus 3. And I'd say, well, is that the same? I'll put a question mark as 12 divided by 4 minus 12 divided by 3, right? If this distributive property works, then it should be just fine. And so 12 divided by, so 4 minus 3 would be 1. So I have 12 divided by 1, which is just 12. And let's see here. Is that the same over here? 12 divided by 4, well, that would be 3. And 12 divided by 3, well, that would be 4. And 3 minus 4, actually, if we were to kind of know what happens later, we'd get a negative 1. And that is not great, right? So that is not great. So yeah, this one down here doesn't work. The one up on top does work. And so because it's only on one side that we can really do this distributive property thing, yeah, we would not call this a distributive property typically. If you are going to go into higher classes, higher math classes, we might say this is a right distributive property because it goes from the right to each of those, but it doesn't go from the left. So that one fails. Okay. So very cool. Very cool. Okay, let's jump back into our screen. Ooh, let's see here. No, let's share screen. Let's get back to the book. All right, what other piece do we have here? That was question 7. Question 8. Let's see here. Question 8. Large collection of marbles. Notice if he borrows 5 from a friend, he can arrange the marbles in rows of 13. Okay. So if he did, then he can get an equal number of rows of 13. Interesting. Okay. Well, rows of 13 would be like multiples of 13. And so since he had to borrow 5 to get there, if you think about each row being 13 long, he would not have been able to make that row of 13. So he would have had 5. He needed 5 to make that. So take a group of 13 and remove the 5, and you'll be right to where he was before he borrowed the 5 marbles. So then that remainder would just be 8. 8 plus 5 is 13. Okay. Yeah. So that was not too bad. I think sometimes people are like, well, I don't know how many rows he had. And the answer is, yeah, you don't know how many rows he had. But in this case, it doesn't matter because they're not asking for how many total. They're not asking for the quotient. They're just asking for what is the remainder in this situation. Okay. Let's see here. Oh, looks like these might be MC. Okay, MC7. All right, let me jump to it here. I think that's what it is. MC number 7. Oh, okay, here we go. For the given computation, answer the following questions, right? Why is the 1 in the quotient above the 2 in the dividend? I think that's the question. From my understanding, I put the 4 in a subtraction represent how many 1,005s are being subtracted. Let's see here. Try figuring this out. And okay, well let's give it a shot. So this is base 10. All right. I'm going to throw some white space in here. Maybe I'll get white space over here and I'll do some white space over here. Okay. All right. Well, let's take a peek at this. I'll do blue for this one. Okay. So when you're doing this division, when you're doing long division, as they call it long division, basically because it is long, not because they intended it to be long. But let's see here. So 4, 3, in this case 43, because we are in base 10, is going into 5,283. So as I do the division, I'm trying to make groups of 4 3s, and I can make them in any place value possible. So first of all, I try to make them in the largest place value, but I just don't have enough there. It's only a 5. So I would write a 0 above it like we did in class. Okay, now multiply, subtract, and bring down. You'd be bringing it down because there's 0 here, and I'd bring down the next number. So now I'm looking at 52, and I can see I definitely get 1. Now you notice that I said 52. Most people do say 52 when they try this, but really what I should have said is 52 what? Like what place value is this? So this is 52 groups of 100. So how many 4 3s or how many 43s can I make in 5,200? And more than that, I think what I would probably say if I was kind of doing this with students is I'd ask how many 100 4 3s are in 5,200, right? Because really that's kind of what I'm doing. So I could see one of them. So when I put a 1 here in this place value, which is above the 2 in the dividend, 1 times 4, 3 is really representing 4300, 4,300. So if I was doing this again initially with students, I probably would write out that I really do have 100 of them, because 100 times 43 is 4,300. That's what's really happening in this algorithm. You'll notice, though, we oftentimes leave those blank, or sometimes you might even see an arrow written down when it's time to bring the next one down. So again, it really is that you're looking at how many 143s are in 5,200. And so there's 100. Now, again, we would typically just write the 1. So the 1 here represents 100 groups of 43. Okay. When I do that subtraction, I'm going to be left with 9. So again, can I make another 4-3 out of just 9? And the answer is no, I can't. So I'm done with that. And then I can bring down the 8. So now I have 43 into 98. And again, I said 98, but in terms of my place value, take a look. The 98 is in the tens place value. So I'm going to ask how many 10 groups of 43 are in 98 tens. And so I can see 2 of them right off the bat. So when I write 2 of them in here, 2 times 43 is 86. When I subtract, I get 1, 2, and I wish I could take another one, but I just can't. It's not big enough. And then I can bring the 3 down. But really, when you think about it, the 2 that I wrote on top is really 20 groups of 4-3, which is really 860, because the number I had above is really 983. And I just took away 860 of them, leaving me with, when I bring the 3 down, 123. And as I subtract, now I want to subtract some more 4-3s. I can definitely see 2 of them. Now those are in the ones column. 2 times 43 is 86. When I subtract, one of these becomes 13. 6 is 7. 1 minus 8. So this is 11 minus 8, so it gives me a 3. And so as I kind of combine all of my place values, my final answer would be 1, 2, 2, remainder of 37. Okay. So why can we just bring the 8 down? The 8 existed the whole time, right? Because all you did is you were subtracting 43 groups of 100. So you didn't have any tens in that place value. And so when you subtract and it says you can just bring it down, it's really because you subtracted 0. You took nothing away. Why can we just bring the 3 down? Why can you just bring the 3 down? Same reason. I have a 0 in there the whole time. So when I subtract, it just comes down without having to change whatsoever. Okay. And what does that remainder of 37 mean? Well, that's one way of saying I just didn't have enough to make more groups of 43. You're trying to make groups of 43, or you're trying to make 43 groups, and I just don't have enough pieces to make that distribution go any further. It's also a quick way you could check it. What we're also saying here is 5,283 is equal to 43 times 122 plus the 37. And you could check that with your calculator, your phone, or another device if you wanted. Okay, let's see here. Next up, what does unique mean? Okay, let's close that. Let me clear my drawings here. There we go. And let's see here. MC, that was number 7. MC number 8A. 8A. What does the 4 in the subtraction represent? Well, there's 2 4s. Again, so I would look and I'd try to define them both. The first 4 that I've listed up here is in groups of not 1s, but 5s, 25, so groups of 125. So that's in my my dividend. And what does the 4 in the subtraction? Because it's a subtraction, I feel like it's this 4 down here. So this 4 is not really just the number 4 in base 5. Look at the place value. This is 4 groups of 25. And then when I bring these two down, this would be two more groups of 5. Okay. And I don't see, yeah, I think that's it. Okay. So yeah, definitely this is a 4. And it really, again, if you want to put all the digits out there, it really is like a 400. But remember, for this problem, you still had a 2-1. So really, if you were going to bring things down, I wouldn't have written 400. I would write it as 421 because that's how much is left over at the end of the day. Okay, let's see here. Next up, what does unique solution mean? Okay, I'm not sure which problem that's on. Huh. Yeah, I don't see one that says the unique part. Am I missing something? Can you respond? Yeah, I think, well, I mean, I can give you the definition. I don't see what question this is on. So there was nothing listed there on your page for that one. And let me go ahead and just share a new whiteboard screen. Okay, we'll jump forward a new page. All right, so here's the idea. If you did watch the videos that I had before, there are times where you can input something into an equation and there's more than one solution. So what we would say is the solution is not unique. Here's a pretty common example, right? 0, not divided by. Let's say 0 times something, and you have to pick that something is going to equal 0. Now you have to pick a number that goes in here to make this work out. So again, you could pick whatever you want. You could pick Michael Jordan's number, 23. 0 times 23 is 0. Okay. But you don't have to. You could have picked, I don't know, another amazing person, little Tom Brady going on. So put 12 in here. 0 times 12 is 0. So what we would say is there's a lot of solutions. We would say the solution is not unique. Okay. If the solution is not unique, it just means there's more than one. When you do a division problem and we say A divided by B is equal to C if and only if A is equal to B times C and C is unique, what we are saying is when you do division, the answer that you get, which is right here, had better be the only possible thing you could get. So if I do 12 divided by 4, I would say the answer to that is 3. And again, I'm looking at this uniqueness thing, asking myself, hey, self, is there ever a time that I can multiply 4 by some number and get 12? And you might say, well, I mean, yeah, there's a 4 times 3. And all I would ask is, can you think of any other number that would go into this box? Because if 3 is the only number that works, then we would say that that is unique. It is the one and only one thing that works, right? Okay, here. I feel like I answered that question. I hope I answered that question anyway. Let's see here. Let's jump back to the book. Okay. And we are question 10. Student claims for all whole numbers AB divided by B is equal to A. Okay. Well, let's take a look. So because we're dealing with division, like I would strongly recommend every time you have a new mathematical concept, kind of go back to what does it mean? What does division mean? Okay. All right, so here we go. Like if I was doing this problem, these are the things I would be asking myself. Saying, hey, self, anytime I have division, and I'm going to write it with some weird shapes, cloud divided by triangle is equal to, I don't know what. Why don't I say star? Okay. So this divided by this equal cloud. What does that mean? If and only if the definition of division says you take your triangle, you multiply by your star, and that has to give you back your cloud. Okay. So that's the definition of division. So when you come down here, your first quantity known as your dividend, here's your divisor, and there's the quotient. Now they're claiming that that's true. So we want to be able to show that it is true, right? So what we're going to do is we're going to say, okay, well, let's take AB and we're going to divide by B, and we're going to say, I have no idea what that's equal to. Okay. I know, I hope that it's equal to A, but I can't say that it's equal to A right off the bat. I have to call it something and then go and do a little bit of work. So again, this is true if and only if AB, which is that left-hand side, is equal to B times D. Okay. So there we are. Now I have a B on both sides. I'll use the commutative property to say basically this becomes AB equals DB. And the reason why I'm doing that is I want to be able to divide by B on both sides. And if they're written this way, I can. So you divide by B on both sides, and these turn into B divided by B, which is just like a number 1. And we know the power of 1. If I multiply anything by 1, I get back the number itself. If I multiply anything by 1, I get back the number itself. So what we've shown here is, hallelujah, that A is equal to D, which means wherever I saw D up here, I could replace it with A. And that is exactly what they wanted us to do right here. So I feel pretty good about this one. Now, again, this is partly as well as your response to the student. But yeah, that's kind of a good thing. So if you need to, put some numbers in, but don't multiply them out right away is my recommendation. So if I said if A is 3 and B is 14, I don't know, I don't want to do 14. I'll say 9. 3 times 9, right? And then you say, okay, I want to divide that by 9. In a sense, if you were to rewrite this like fraction form, then you could say, well, wait a minute, I have the 9s here because they multiply and give me the magical 1. So I get back to 3, which happens to be the number that's first, which the number that's first over here is A, and that's what I was supposed to get back to is A. So it all comes kind of full circle. There is 10. All right, let me clear my drawings off. Yeah, let's see here. Any other questions? Question 16. Okay, well, let's take a look at 16. Yeah. Let's see here. Does the pattern continue? This goes back to one of the other questions that was in the homework where you had the A minus B times A plus B. So this question 16 is a pretty good one that you should be kind of asking yourself as well. Again, it does link back to the algebra. So let's throw a little white space in here. We'll throw a little white space over here. And okay, so yeah, let's see. Your student notices 39 plus 41 is equal to 40 plus 40. Yeah, and that's okay, because remember, 41, you can decompose 41 at any time into 1 plus 40. And so if you really had 39 plus 41, what you really have is 39 plus 1 plus 40, and that should make sense because that's still the same as 41. And then you use the associative property and you get 39 plus 1 plus 40, and you end up with 40 plus 40. So it works out really nicely. But if you do multiplication, it won't work. And you might be able to see that right off the bat here, because 40 times 40, you know it's got to end in a 0, but 9 times 1 does not end in a 0. Okay, so when you're doing your ones place, it's definitely not going to work out for you. Yeah, I think that's about it for that one. Okay, let's see here. The piece I was referring to is the a plus b times a minus b, and how that has to equal a squared minus b squared. And so what you can look at is if you want to kind of be able to compute this directly, notice they say 39 times 41 is equal to 40 times 40 minus 1. Take the 39 and say, well, I wonder if 39 could be over here on one side. And 39 turns out to be exactly the same as 40 minus 1. So if I write this as 40 minus 1 right there, that is 39. The other one would be 40 plus 1, which looks, again, pretty reasonable. And then, and if you subtracted 1, that would be 39. If you added 1, that'd be 41. And then you just multiply those together. But what's great is if you leave them without kind of doing all of that math, you could rewrite this as 40 squared minus 1. It's really 40 squared minus 1 squared because that's 40 minus 1 times 40 plus 1. This part then becomes the distributive property. And 40 squared, if you think about it, is like 40 times 40. So forget about the zeros momentarily and just think about the 4 times 4. And then you'll be able to say, oh, that's 16. And then I had a 0 for each of them. So a 0 for the first one, 0 for the second. And so I get a couple zeros on here. And then you get to take 1 away, which is a whole lot quicker than typically trying to multiply all the numbers out. Okay, so taking a look here, you have a little basis here. Don't forget, algebra is our friends. If nothing else, if you struggle with the algebra, we need to get good at algebraic thinking, which ties together the way we process information, the way we attempt problems, and kind of how the problem ends up going in the textbook. All right, that's it. So thanks for sending in the questions. Keep them coming. I had a pretty cool day in class. I hope you did too. Got to see some stuff with the chips with both multiplication and division. And again, if you've got questions over the weekend, let me know. If you need to meet up, I can meet up in person. I can meet up on Zoom. The choice is yours. All right, off you go.